So we're talking about design robotics, and just to give you a very brief introduction, this is a 5-year research project funded by the Innovative Manufacturing CRC, IMCRC. It involves QUT and RMIT as university research partners, and it's funded by our industry partner, UAP. And to give you an idea of the kind of work that we've been doing in the project, I'd like to just talk about the image you can see here on the screen. This is a staircase that was manufactured by UAP for the University of Technology, Sydney business building, and it's designed by a leading architect, Gehry Partners, and it uses the latest kind of digital design techniques to create this amazing swooping form that you see here. But there's a real problem for a company like UAP that has to manufacture these things. How do you take those amazing digital designs and turn them into reality? So we've been working with UAP to find ways to give robotics the kinds of capabilities that are needed to make this kind of very bespoke, mass customized manufacture possible. That's probably enough to get us started, and I'm going to hand over now to John, who's going to start telling us about robotic vision.
Hi everyone, so I'm Jonathan Robertson. I'm a chief investigator on the project. We've got a section here where we're going to talk through robotic vision. I'm going to start off with a bit of an introduction. I'll then hand over to Amelia, who's next to me here. We'll then hand over to Jing, and finally over to Peter Cork, who's back in one of our labs at QUT. So you can see here a picture of an installation. This was an artwork by artist Lindy Lee, and it was fabricated with our collaborator UAP, and this was actually fabricated in the shed next door to where we are today. What I want you to see is or look at is the screens on the right hand side. These are flat sheets, and these holes and the patterns that you see there are put in by Lindy Lee herself. But there's some work that has to be done first before she can sort of get to work and designing her artwork, and that is a technique called linishing. So these panels have to be prepared. Now, this is backbreaking work. It's very time consuming. You can see a tool there, which is known as a burnisher, and we'll show you one of these on one of our robots in a little while. It's effectively a sanding task, and linishing just stands for linear finishing. And an operator here, in this case, this is Matteo, who is based at UAP. He has to stand there and linish this panel by hand, and it's very time consuming. So I'm going to show you a video now of a robot version of this linishing task. So Matteo came to the team here and said that he had to linish, I think it was 8 of these panels, and he knew it was going to take him a very long time. The estimate was about 24 hours per panel of him holding the burnisher, which, as you can imagine, is a lot of backbreaking work. So Matteo worked with Amelia, who you'll see in a little while. They worked for 3 days and designed this robotic solution. So you'll see Matteo's still there. He's still part of the job. He's no longer backbreaking most of the time. He's he's lubricating, he's changing sandpaper, he's checking things out. He's actually dragging the robot along. That's not a motorized system there. And then the robot is actually doing the linishing task. Now, this is a relatively simple task for robotics. It's a 2D plate. It's known as an open loop system in the fact that the robot doesn't really know the plate's there. It's just been pre-programmed to go up and down, which means it actually misses some of the plate. So if you look at the bottom of that plate, you will see some parts that have been missed. And that's where everything's slightly misaligned and the robot doesn't quite touch, or it can't reach. There's a few reasons why it may miss, but it's basically the robot doesn't really know that the plate is there. So we're trying to increase the sophistication. We've now moved on to then doing 3-dimensional finishing. Now you'll see here an artwork called The Kingfisher. This is by an artist called Emily Floyd. And again, this is fabricated at UAP in the shed next door. And we've been focusing on finishing the feet of this bird. This particular bird is actually on the river walkway outside our building at QUT at Gardens Point here in Brisbane. And I should have put someone in there for scale, but it's kind of the height of a shortish adult. That's the kind of the scale of this thing. So where you can see this, this foot is relatively complicated, and just having our kind of open loop systems wouldn't be good enough to actually finish this foot. So now I'm going to hand over to Amelia, and she is going to talk through our strategies for finishing 3D objects like this.
Thanks for the intro, John. So as you said, I'm Amelia, and I'm a mechatronics engineer as part of the Design Robotics project. So this first video here is actually a 3D scan of the bird foot that you just mentioned. So it's quite common in manufacturing companies to actually have a 3D model of whatever thing they're about to manufacture, but it's not common for people to actually use it in the manufacturing process. So what we've tried to do is, one second, let me. True robot demo fashion. Hope it works.
Let's start
there
the
we
robot.
go.
There you go.
Yes. So what we've tried to do is actually incorporate 3D scanning for two real reasons. So the first one being when you actually have a perfect 3D model of a piece that you want to manufacture, it's not actually perfect, because when you manufacture, or how to actually come about making a physical model, typically involves some kind of, in this instance, casting process. And in this case, we actually mill it out using a robot, another robot, not this one here, to make a mold, which then goes into a sand mold and have molten aluminium go through and evaporate that mold to then give us the product that you see that the robot is currently scanning. Once we make that first mold, it's actually used as a template for future molds. And then as you do that, it actually shrinks by nature of the process. And so this perfect 3D scan that I will now show you, go back to, this one. Yep. So this model that we were showing before is actually slightly larger than what we actually have. And of course, this scaling or this shrinking is never uniform, so it's always a little bit annoying when you're trying to use it in the actual process. So that's the first reason for using 3D scanning. And then the second is we actually need to be able to locate where this piece is in space with respect to the robot. What our 3D scanning does in that demo I just showed you is given a very rough estimate of where the bird foot actually is in space, and a very rough guess as to the size of this object, so putting it in a bounding box, what we can do is generate a grid of points that the robot will visit and capture snapshots of what the object actually looks like. So what we can see here in the red box is actually just, in this instance, I think it generated 15 points based on the camera's field of view. Those are just 4 snapshots there. And you can kind of see that with 3D scanning, I'm not sure how familiar people are with this, but 3D scanning, shiny, reflective, specifically metallic objects is always difficult. And of course, your environment is also, it impacts quite significantly. As you can see here, there are like these little holes. But what we're able to do is if we capture enough of these, we can actually stitch them together, which is what the top right scan is here. And then it completes a somewhat complete model of what we actually need to deal with. And then this model on the bottom here is just a filtered version, because it's just a very dense point cloud, and that involves a lot more computing processing power that's not necessarily useful. But this is also just a little video that I made that shows that it's stitching together. And this is just purely based on knowing where each of these grid points are. We can just put all of those little snapshots together. And then this is just a little video of what the filtered scan looks like. Yeah. So once we actually have a scan, what we're able to do is actually that we need to actually lineage it. So of course this involves path planning, and we actually do this through Grasshopper or Rhino. And what we're able to do is essentially segment this model and then actually generate points, and then we can actually execute them using force control at the same time. But of course, this being an automated process, how do we actually know, and also what John was talking about before, how instead of having an open loop problem, we would ideally like a closed loop problem where the robot can actually get feedback and then figure out when do we actually need to stop. So that brings us to Jing.
Oh, hi everyone. Thank you, Mia. So, yeah, I can share my screen here. Hi. Right, hi everyone. I'm Jing Ping. I'm a research fellow in design robotics. And the topic I want to share with you today is how to check surface roughness of the workpiece during robotic grinding and polishing with the neural network so that the automation system knows when to stop. And so to solve this problem, we need to think about 3 elements. One is surface roughness measurement. So it's an in situ surface roughness measurement with neural network. One is pneumatically controlled robotic grinding and polishing. Another one is automatic part planning according to the workpiece. And this figure shows our test images of our neural network. Firstly, we used pictures of rough, medium, and smooth surfaces to train our neural network. And then we used different pictures to see if it can put the images into the right surface roughness categories. And for pneumatic control, like this soft actuator here, applying a certain force, a certain down force to the workpiece with physical compliance, and this orbital air sander, like this one here, and so can both be pneumatically controlled. And so our application is like this: a robot with a camera. When a robot with a camera see the workpiece, it can automatically do a path planning and follow the path. And then it would take pictures of the surface and run the pictures through the neural network to measure the surface roughness. If it's rough, it can continue grinding. If it's medium, then it can adjust its processing parameters, like the speed and the rotation speed. And then when the surface is smooth enough, it can stop running and be back to its rest pose. So in our application, we need to implement one control loop to control the soft actuator to achieve ideal downforce of processing, and implement another control loop with computer vision to control the processing parameters and when to stop the automation system. So as you can see it here, so it runs and so it can stop. It like the electric kettle. You press one button and the water is boiled and the kettle is turned off. So you can leave the workpiece there unless the robot finishes its job. Our solution has applications not only in like polishing and grinding, but also in areas like welding and painting. Like the robots can do boring and dangerous jobs, while people can do more creative jobs like designing, and work collaboratively with robots. Yeah, thank you for your attention. Now let's welcome our distinguished Professor Peter to talk about robotic force control.
Thanks, Jing. Let me just share my screen. All right, people can see that? Good. All right, so what I want to do is just bring together some of the topics that have been mentioned by Jing and Amelia, and what are the real challenges for doing this with robotics today. I mean, robotics is a mature technology. It's 60 years old since the first robots entered manufacturing plants. But we still don't see robots routinely doing these jobs like linishing and grinding and so on. So, why is that? So I just want to touch on some of those questions. So to do a task like linishing, grinding, polishing. At the moment, it's done by a human who picks up the tool, applies it to the workpiece, and does the job. And to do this, it involves actually much of our body. It involves our eyes. We're looking, we're using our arms, the muscles in our arms to hold the tool and apply it, our hands to grasp the tool, and our brain is doing an awful lot of work here. So it's not just manual work, it really is a whole body exercise. Eyes, arms, hands, and brain are involved in doing this. So if you were, even if you're unskilled at this, but you were asked to grind a piece of metal, the first thing you're going to do is you're going to pick up the tool, and then you're going to try and find the thing that you need to apply it to. And this is probably an exaggeration. Probably the workpiece is mounted on some pedestal on the factory floor. But you need to know where it is. And human beings are remarkably good at recognizing objects in the world. And Amelia showed some examples of building a model of an object that perhaps we don't know the shape of in advance. We can use laser scanners and RGBD cameras and things like that to give us the shape of the object and the position of the object. And once we've got that information in what we call a 3D point cloud, we can then compute not only what the object is, where the object is, but we can also compute the orientation of its different surfaces. And so over on the right-hand side, there are all those needles, and they're basically normal to the local surface of the object. And so that's pretty good then. If you've got a camera system, you can recognize the object, it can work out the orientation of the surface, then we can bring the tool toward the surface, we can orient it correctly in space, and off we go with our operation, our grinding or our linishing. Now, robots today, and some of the ones that you saw in the videos, are the ones that you can just go to the shop and buy a big industrial robot. They are remarkably capable machines. Modern robots are very strong. And here's a data sheet for some KUKA robots. And you can see these robots have got payload capability up to 360 kilograms. You know, that's an enormously strong machine, way stronger than a human. And they're also incredibly precise. So this machine that can lift 360 kilos can position the tool to within 0.08 of a millimeter. So strong, fast, precise, and the other advantage of robots, of course, is that they are relentless. They go 24/7 and they won't get tired. So if I've got sensors that tell me where the object is and how it's oriented, and I've got a robot that's strong enough to wield the tool, is that enough? And I'm going to say, no, it's not, because there's always going to be very small errors. The camera is not very precise, and the camera only says where the object is with respect to the camera. And the problem is we don't know where the robot is with respect to the camera. And so if you have a very small error, say you're out by 0.1 of a millimeter, your linishing drum is 1/10 of a millimeter above the surface, then you're not going to do any grinding at all. You're not going to do any metal removal. And John showed an example of that at the bottom of that vertical plate. On the other hand, if you're 0.1 millimeter too low, then you're going to be gouging out a lot of material. And that's going to damage the surface. It's going to damage the finish. So that's not very good. You want the Goldilocks solution where the linishing drum is just right. And so how is a robot going to do that? Or more interestingly, how does the human do that? And the human does this by using hand-eye coordination at one level to bring the tool close to the object. You use your hand in your eye and you minimize the error. And so the human being isn't measuring coordinates in X, Y, and Z. The human who's threading the cotton through the needle, they don't know the position of the needle or the position of the cotton. They just want to make the difference between those positions equal to 0. And that's a really important principle that we need to bring towards robotics. So we use this hand-eye coordination skill. But the other skill that we use in an operation like grinding is that we control the force that we apply through the tool to the workpiece. And that's really critical. And in our body, we use information that comes back to us from all the nerves that are embedded in our muscles to measure the force that the tool is applying. We can feel the vibration through our fingertips, and we also use that to control what we're doing. And we also hear the noise from the grinding process through our ears, and we feed that back into the process. So we're using all of this rich sensory information to control the intensity with which we're doing the material removal operation. And that's what's key. And that's why a standard robot, although it's very strong and very precise, the problem is the robot's precise, but we don't know precisely where the thing it's working on is. That's the real challenge. But if we can modulate and control the force that we apply, then that problem goes away. So that then brings us to this new generation of robots, often called collaborative robots. This robot here is able to measure the force that it exerts on the world. And here you see it inserting a SIM memory module into a circuit board. And you can see that it's wiggling it around just like a human would do. It can measuring the forces that are exerted. It knows when it's finished. It's not going to push the memory chip through the board because it knows when it's exerting enough force and it will stop. And so this robot has got sensors in all of its joints, and that allows it to understand the force that it's exerting on the world. So this is the sort of technology that we need to combine with computer vision and with Linishing tools applied to problems in manufacturing. So that's the challenge. This is why it's not easy. I'll stop there. Thank you.